Okay, so we started this unit looking at probability, and we looked at mutually exclusive and not mutually exclusive. So this should go on like a study sheet or just some, I don't know, somewhere. Because I just. Okay.
It's blue.
How's that? Okay. Is that okay? Okay. So tell me what it means when we're dealing with situations that are mutually exclusive. They're nothing to do with. So give me an example of mutually exclusive things. Eating a peach, eating an apple. What was yours, sorry? Picking a random number and then also picking a card. Okay, totally separate. Wearing a shirt or wearing no shirt. Right? That's mutually exclusive. Two things are met. So when we're dealing with mutually exclusive, is this an or situation or an and situation? Let me find the probability. It's an or situation. It's an or. So we're dealing with the probability. So this is A and B. Probability of A or the probability of B. When we're dealing with A and they're mutually exclusive, what do we do with our probabilities? How do I find the probability of A or B? Add them. So probability of A plus the probability of B. So keywords is, right, one of the keywords here is or, obviously, one or the other happening, or both like you want, they're dealing with events that they're not related. So not mutually exclusive is when now we have the overlap of A and B. And so what would be the formula now instead for probability of A or B occurring? So now we have probability of, what's wrong here? What do we have? What's this middle part called? The intersect, so what would it be? Or actually, I'll just fix it. So what's this right here? That area in between here. It's A and B. A and B. And so when I add A plus B, what happens? If I add A plus B. Your number's too big. Why? Part of A is shared with part of B. And so if you add A plus B, that overlap, you end up adding it an extra time. So to compensate, what do we have to do? Subtract the A and B. So then we went on to dependent and independent events. Okay. Does everyone have the top written down? Yeah, can I scroll down a little bit? Okay, so tell me the situations that we're dealing with, dependent situations. Dependent. Okay, so when the first probability affects the second probability. And the first probability affects the second probability. So give me one of the key words that you are going to spot when you're dealing with dependent events. So it's dealing with and. Yeah, so we want a diamond and then another diamond. What else has to happen? What is really important for that? So that A affects B. Replacement or not replacement? Not replacement. So not replacement. So when we're dealing with those cards, we're not replacing. We're picking socks, we're not replacing. Spell that right? I think so. So not replacement. And it's an and situation. So we want A and then B to occur. So what does our formula look like? Dean, what's my formula then? Probability of A and B occurring in a dependent situation. So the and, what is it going to be? What sign in the middle? And is multiplication or is addition. Okay, so it's going to be a multiplication. So we want to multiply A with B, but what's special about B? How do we write this one if it's dependent? Yeah, given that A has occurred. So that means given that. Given that A has occurred. And sometimes it's going to ask us to find a question where find the probability of B given that A has occurred. So we just rearrange this formula. And so what would the formula look like if I want to solve for given the find the probability of B given A has occurred? What would it look like instead? Brad? So what would it be if I want this guy by itself? What would you have to do to both sides? If you want, if this is multiplication, divide both sides by probability of A. So it would be probability of A and B over the probability of A. So sometimes you might have to rearrange that formula. So if you know this one, you can easily rearrange it. Okay. And then today we're going to deal with independent events. And they're a lot easier, actually. Why might it be a little bit easier? They're separate. So the first probability, does it affect the second? No. The first probability does not affect the second. So what kind of keyword situation will you see here if it's like cards? So you're dealing with and again, yeah. So we're going to pick a diamond and a diamond again, given that it's replaced. So replaced. It is replaced. So there is replacement. So it's still and. Yeah, it's still and with independent or dependent events. So A and B occurring, but the only difference is it's just the probability of A times the probability of B. Okay, and often, very often, you can use them for dependent, but very often we're going to use a tree diagram for independent. We kind of looked at one yesterday, and we'll look at a bunch today. Okay. Now sometimes we're going to have problems that might have to deal with and or situations in the same problem, right? So you figure out, you'll see, we'll get to some. So you have to, just like that question you did on your quiz, right? Where you had to do white then black, and then black then white, and then add them together. Okay, so that's our quadrant. Quattro. Never mind. Might not get that reference. So let's start the lesson. Okay, I would like you to look at this. We've got Cam and we got Emily. Cam and Emily. 3.6. The Fortin family has 2 children. Cam determines the probability that the family has 2 girls. Emily determines the probability that the family has 2 girls, given that the first child is a girl. How are these probabilities similar and different? Yeah, okay, so let's just use the basic 50%. Okay? Basic, like, got a 50-50 chance of having a boy and a girl. Well, if you look, Mentally, it does work out that way pretty almost, if you look at the world's population. But yes, and in some families, as much as they try, same, right? 'Cause it depends on the guy. Yeah. Well, they're changing the laws. It used to always be that it's not that they don't allow girls, is that they, because of this large population, they only allowed one child. And to carry on your name, it would have to then be a boy. And so if they wanted, no, they don't. But it seems like that. That's very. Oh, sorry. Yeah. Okay, so let's look at Cam. So basically, Cam's saying, what are the different ways we can have two children? You can either have a boy and a girl, one boy and one girl. You can. What else could you have? Two boys or two girls. Okay. So Cam says, this is basically how Cam's figuring it out. Cam says the probability is of having, so we have these three combinations with the probability of having two girls. 1 out of 3 based on what. Now, what did he do that Emily doesn't do? Or let's do Emily's first. Maybe then you could see. Nice. So does order matter for Cam when he's looking at it? No. But for Emily, it does. Okay, so what are the different orders you can have for two children? What's the orders? Give me one order you can have for two children.
Boy, girl.
Boy, girl. Okay, first a boy, then a girl. Then a girl, and a boy. Boy, boy. Girl, girl. So what is Emily? So we were doing two girls, right? So what's Emily's probability? 1 out of 4. And so if order does matter, it affects the probability. If order didn't matter, right? So that's our difference between perms and comps. We looked at that last unit. Okay, so I'm going to grab my notes. You finish getting that down, and then we'll look at the next bit. Got it down? We're good to go? Almost. Okay, so in this problem with Emily, not looking at genetics and that kind of stuff, Sawyer, does the probability of having a boy first, is that going to change your chances of having a boy second? No. So are these independent or dependent? Independent here, right? So another way you could have calculated is, right, we have, what is the probability of having a girl first? What's the probability of having a girl first? No, just first. Just one over, what's your probability of having your first child as a girl? 50%, 1 out of 2. What is the probability of now having your second child as a girl? 1 out of 2, still 50%. It's either a boy or a girl, which gives you what? Which gives you? Okay, so which gives you 1/2 times 1/2? 1 out of 4, right? It's another way we can solve this problem. Okay, so this was girl, then times girl. Probability of a girl times probability of a girl. You solve it either way. So in all our problems here, like the order does matter. Key ideas. So here we're dealing with, we already talked about this definition of independent, so we can move on, right? Yes? You with me, Sawyer? You're with me? Okay, so here's our formula. You already wrote it down. They're independent, so let's go on. Woo! Okay, Okay, so what I'd like you to do, because we've talked about the difference between independent and dependent, I would like you to go through these 4 examples, and you're just going to write, is it dependent or independent, and why? You can do this with a partner if you like. You spend like 2 minutes tops on this. Okay, so first one we already talked about. Does spinning affect your roll? The answer is no. So the answer is independent. So our explanation or justification is, I wrote it, rolls don't affect spins, and vice versa. Oh, don't know. Okay, a red die and a green die are rolled. The first event is rolling a 1 on the red, and the second event is rolling a 5 on the green. Independent or dependent? Do we agree? Who says independent? It's independent. 2 separate dice. Yeah. They're 2 separate dice. Die. 2 separate die. Okay, 2 cards are drawn without being replaced. Dependent. What's our reasoning? Right there. We did not replace it. There are 30 cards, numbered 1 to 30. 2 cards are drawn, 1 at a time, with replacement. Therefore, that's independent. And it's right, there's our reason. Okay. Okay, we only have 2 examples left. And we're done our examples. Okay. So we are dealing with Anne and Chantel. And they decided to play a little game because they're bored. They had a die and a coin. Each turn consists of rolling a regular die and tossing a coin. Points are awarded for rolling a 6 on the die and or tossing heads. Now, is the situation independent or dependent? Does rolling your dice affect independent? Okay. So this one asked me, determine the probability, and the wording is not very good here, but that Anne will get a 1 point. We're going to do them all separately. So we're going to find the probability she gets 1 point, the probability she gets 3 points, and the probability she gets 0 points. That's what we're looking for. Because the probability of 1, 3, or 0 would be 1, right? If we did them all together, it would be 100%, because it's either 0, 1, or 3. So what I wanted to ask here, which is not very clear, yeah, so we're going to do them separately. What's the probability of getting 1 point? What's the probability of getting 3 and 0? Now, independent problems work really well with a tree. Okay, so what's the first thing we're doing? What are we going to do first? We first roll a die, roll our dice, and then we're going to flip a coin. So there's always 2 situations in these independent. So we have our die and then our coin. Okay, so what outcome? Points are awarded for rolling a 6. So what are the 2 outcomes with your dice? Either you roll a, okay, so with your dice, 6, either you roll your 6 or you don't roll your 6, so not 6. Either you roll a 6 or you don't roll a 6. Because you only get a point if you roll a 6. Right? Now we want to fill in our probabilities. What's the probability of rolling a 6? Actually, 1 out of 6. So what's the probability then of not rolling a 6? 5 out of 6. These 2 should always add to the total of 1. It's either one or the other. Okay, after that, with the coin, what are the two situations? Head, so probability. Now, when does she get a point? She gets a point if she gets a head. So we have heads, or the other option is not heads, which is, or you can also call that tails. Or you could even call it not heads. Either or is fine. Right? The reason why I'm doing heads and not heads is to show one's favorable, one's not favorable. Oh, it is warm now. It's like, yeah, it's like burning the dust. Okay, what's the probability of rolling a head? 1 out of 2. What's the probability of not head? Not getting a head. Probability of a head again, 1 over 2. Not rolling a head, or tossing actually. Okay. So what situation is this here? What situation's here that led to here? So here, you're going to have to move. Dean, turn around. So what happened to get to here? Look at the tree. You rolled a 6, and then you rolled a 6. So how many points did you get here? 3 points. So what's the probability of rolling a 6 and then a head? How do we get it? How do we get from, we want this and this to occur. Multiply them. 1/6 times 1/2. Oh my gosh. Is anyone else dying? Melting. I should turn down the heat. Okay, what's 1/2 times this? What? 1/2 times 6. 1 over 12. Okay, let's keep going. What outcome is here? What outcome is this? 6 and not a head. How many points do you get that? For that? 1 point. What's the probability of that occurring? 1/12 again. 1/6 times 1/2 gives us 1/12. Yes. Yeah. Thank you. Okay, what's happening here then? Let's get to there. No point, so not a 6, and well, and a head, so how many points is that? 1 point. What's the probability of that occurring? No. Now we're going, what times what? 5/6 times 1/2 gives us 5/12. I don't know about that. I would disagree with you, actually. You're more likely to get 1 point than no point. At least 1 point than no point. Okay, what's the probability of no point? So not a 6, not a 8, head. Because there's 2 of these, so we would add them together. No. Here, I'll show you. So it's 5/6 times 1/2, which is 5/12 again. So here's my situations where we're getting 1 point. So 1/12 chance or 5/12. So together, that's a 50% chance of getting 1 point. Only 5/12 chance of getting no point. So better chance of getting a point than no point. Okay, so what's the probability of getting 3 points? What's the probability of getting 3 points? 1 out of 12. Good. What's the probability of getting 1 point? 1 out of 2. How do we get that? Yeah, we're adding, these are two situations where we had 1 point, so we're going to add them together. One or the other occurs. So 1/12 plus 2 5/12 equals 6/12 or a half. And last, what's the probability of getting no points? 5 out of 12. Now, how do we know that our answers are correct? What can we do as a check? Add them all together. These all add to 12 out of 12. Or 1. Yeah. Dean, why should this all add to 12 out of 12? Is there any other situations available?
No.
No. These are all the different combinations that could occur, so total adds to 1. All right, one more. Do you want to do it on your own?
No.
Okay, well, here's your choice. Together or alone?
We have like 5 minutes left after this.
Where is it? Oh, yeah. Okay, 1,000 tickets. After doing this example, you might feel like you'll never buy a 50-50 ticket again. All 1,000 tickets for a charity have been sold and placed in a drum. There will be 2 draws. The first draw will be for the grand prize, and the second draw will be for the consolation prize. After each draw, the winning ticket will be returned. Why is that important? If you're talking, it's replacement. If your ticket's returned, there's replacement, meaning what kind of situation do we have? Independent. Independent. What often works good with an independent situation? A treat. Especially when there are two situations. Okay, Max has bought 5 tickets. Determine the probability to, determine the probability to a 1/10 of a percent that he will win at least 1 prize. Okay. Grand prize. Oh yeah, we're good. So what's the 2 situations for the grand prize? Either you win or you lose. Not win. Okay? So what is his chances of winning the grand prize? 5 out of 1,000. What can that reduce to?
0.005.
Yeah, which is also, as a fraction, over 200. I'm wrong. So 5 out of right? He bought 5 tickets. Thank you. 5 out of 1,000. What's his probability of losing then? No. If his probability of winning is 1 out of 200, would be 199 over 200. These 2 should add to 1. So then comes the consolation prize. You can either win or not win. Now, Dean, you're saying they're the exact same. Why are they the exact same? They're independent. Now, you could even use a tree if it's not. If it was dependent, you would just adjust these guys.
Question. When the guy raffles the winner, does he put it back in the raffle?
Yeah, he puts it back.
Oh, okay.
So that's why it's independent. So now it's still 1 out of 200. For charity. It's for the children.
No, wait. If one person wants to choose things, he'd be the most hated person.
I know, hey? You totally would be. But let's see how likely that is to occur. Okay? So here, what situation is this very top one?
What?
What's the situation with this top part of the tree? To get there, he had to win the grand prize and then win the consolation prize. Crazy. Okay, so how do we calculate the probability of him winning both? The first and the second. And's a key word. How do we get that probability? So here, I'm going to move you.
I'm just fixing the wrinkles. It's driving me nuts.
Okay, then come to here.
Oh.
Okay, Andrew, how do I get the probability of winning and winning? Times them. Winning and winning. Well, win and then win again. Winning, which equals, actually that's really, 1 out of 40,000.
Wow.
That's not very likely. That is better chances in the lottery. There's less tickets here.
Miss Johnson,
Yeah,
I just have a probability question that I wanted to figure out a while ago.
sure.
Okay.
Okay, we'll do our best. So what's the problem? So what's happening here to get to here? Okay, Spencer, what's happening here? He wins and then he doesn't win. So it'd be 1 over 200 times 199 out of 200, which gives you 199 out of 40,000.
If you win the first prize, it'd just be embarrassing with the second prize. You get like, okay, ooh, you suck.
Yeah, and it's very unlikely that that will ever happen. You'd almost want to give it away, hey? Because the gram, who wants cancellation when you can have the gram? Anyways, who needs that? Okay, figure out the next two on your own. Figure out the next two on your own. Dean, you're not leaving until this is down.
I'm a visual learner.
My probability question is going to be the
So you should have had.
It's all about work ethic. You don't like your job, who cares? Get over it and make money.
It's a very mature thing to say. Okay, and the last one. What's the probability of losing? A lot. Okay. Well, unfortunately on your test, even though it's a lot, you actually write the number. You can't just say a lot.
Why not?
So 39,601 out of 40,000. Very, very, very light. You could have you could also have added these three together and subtracted 40,000, right? From 40,000, that would have gave you this number as well. Okay, what's the question asking? The final question. What's the probability that he does what? At least one. So what's the situation when you win at least one? Which one of these are you winning at least one? Which ones? Which ones? Okay, the middle. What about the top? Are you winning at least one? Yes. Well, at least. At least is minimum of one prize. So you can win two. Okay, so how are we going to get the probability that we win at least one? We add them together because it's, can you do both at the same time? Can you win two and one? No, it's either you win two, both of them, right? Or you win the first or you win the second. So we're going to add them together. So the probability you'll win at least one is 200, so 399 out of 40,000. What is that as a decimal? Okay, 0.009. So as a percent, not even 1% chance. And that's with 5 tickets out of 1,000. Yeah. Okay. Do you want to write it on a piece of paper?
Can I just say it to you? It's really easy.
Okay.
Okay. So there's this, for